Hey everyone, welcome back to the channel. In this video, we're going to deconstruct the research paper Learning Performance Improving Code Edits by researchers from University of Pennsylvania, Carnegie Mellon University, Google, and Google DeepMind. I was first introduced to this paper by Amir Yazdanbakhsh during MENA ML 2026. For those who are unfamiliar, MENA ML is a machine learning winter school that has had 2 iterations so far. The first edition was held in 2025 in Doha, hosted by Hamad bin Khalifa University, while the second edition took place in 2026 in Saudi Arabia and was hosted by King Abdullah University of Science and Technology. If you want to learn more about MENA-ML, you can check out the official website. Now, coming back to the paper. In this video, we are going to focus on 2 main questions. 1. What problem is this paper trying to solve? 2. How does the proposed approach actually solve it? We'll break down the ideas step by step, discuss the intuition behind the method, and understand why this research is important in the context of machine learning and code optimization. So, let's get started. The paper is solving the problem of automatically optimizing computer programs for better performance using large language models. More specifically, it focuses on improving the execution speed of code while keeping the program functionally correct. Traditionally, compilers can optimize low-level details, but high-level optimizations such as API and algorithm changes still require human programmers because they depend on understanding the semantics of the code. The authors wanted to answer this research question. Can pre-trained large language models automatically learn to optimize programs the way expert programmers do? To solve this, they introduced 1. A new benchmark dataset called Pi. 2. Reliable performance evaluation using the GEM5 simulator. The reason for using the GEM5 simulator is that measuring execution speed on real hardware is noisy and inconsistent due to system load and operating system behavior. So they also address the problem of reliable and reproducible performance measurement for program optimization research. 3. Several techniques for adapting LLMs for code optimization. Now moving on to how Pi dataset was constructed. The authors built the dataset using competitive programming submissions from the CodeNet dataset. The goal was to collect examples where programmers improved the performance of their own code over time. So step 1 was collect C++ programs. The reason was C++ is performance-oriented and it works with the GEM5 simulator. Step 2, track program submission history. For each programming problem and each user, they collected all submissions in chronological order. Here, each YI is a program submission by user U. This forms a trajectory showing how the programmer improved their solution over time. Step 3, remove incorrect programs. They filtered out programs that 1. Failed test cases, 2. Or exceeded the time limit. To ensure correctness, they used original CodeNet test cases plus additional test cases from DeepMind Alpha code. Programs were rejected if even one test case failed. This improved correctness verification. After filtering, they obtained only valid accepted programs. Step 4. Create program pairs and keep only significant optimizations. From each accepted trajectory, they created pairs such as Y1Y2, Y1Y3, and Y2Y3. Each pair represents a slower version and a faster version. They only kept pairs where the later program was at least 10% faster. This ensured the dataset contained meaningful performance improvements, not tiny or noisy differences. Step 5. Recompute runtime using GEM5. Although CodeNet already included CPU times, the authors found them unreliable. So they reran programs using the GEM5 full system simulator and recomputed execution times. They performed 42.8 million simulations in GEM5. This gave deterministic reproducible runtime measurements. Step 8. Split into train validation and test sets. Finally, they split the dataset into training, validation, and test sets. Importantly, the same programming problem was never shared across splits. Final dataset sizes were, for training, 77,967 pairs from 1,474 problems. For validation, 2,544 pairs from 77 problems. And for test, 978 pairs from 41 problems. Now, let's move to the third section of the paper. This section explains the different approaches the authors use to improve code LLMs for program optimization. The main idea is, how can we prompt or train an LLM to generate a faster version of a slow program? The authors experimented with several prompting strategies, and they also explored fine-tuning to further improve performance. The first prompting strategy is called instruction prompting. This is the simplest approach used in the paper. In this method, the model is directly instructed to optimize the code for better performance. The LLM relies only on two things: its pre-trained knowledge and the instruction provided in the prompt. No examples or demonstrations are given to the model. The second prompting strategy is called few-shot prompting. Instead of giving only an instruction, the authors also provide examples of optimized code directly inside the prompt. The prompt follows a structure like this: slow program to optimized program, slow program to optimized program, and then finally, now optimize this new program. For example, the model might first see a slow implementation using nested loops, followed by a faster version that uses a hash map solution. After seeing a few examples like this, the model is then asked to optimize a completely new piece of code. So, what is actually happening here? The model starts learning from the examples provided within the prompt itself. This is known as in-context learning. Instead of learning through training updates, the LLM learns optimization patterns directly from the context of the prompt. It tries to imitate the kinds of transformations shown in the examples. Next, the authors experimented with chain of thought prompting. In this approach, the model is asked to reason step by step before generating the optimized code. The idea behind this approach is that forcing the model to think through the optimization process can lead to better and more accurate code transformations. The fourth and most powerful prompting strategy is dynamic retrieval-based few-shot prompting. This is one of the key ideas in this section. Instead of relying on fixed, manually chosen examples, the authors dynamically retrieve the most relevant optimization examples directly from the Pi dataset. The core idea is simple but very effective. Different programming problems require different optimization strategies. For example, dynamic programming optimizations tend to help other dynamic programming problems. Graph-based optimizations work better for graph problems, and sorting optimizations are more useful for sorting-related code. So instead of randomly selecting examples, the model retrieves similar programs that are actually relevant to the input problem. Now, how does this retrieval process work? First, the authors convert programs into embeddings using CodeBERT's core models. This transforms each program into a dense vector representation that captures its structure, semantics, and coding patterns. Next, the new slow program that needs optimization is also converted into an embedding using the same method. After that, they use Facebook AI similarity search to efficiently search for the K most similar programs from the training dataset. Finally, they construct a dynamic few-shot prompt using these retrieved examples. The prompt looks like this. The important thing here is that this prompt is not fixed. It is created dynamically for every new program based on its similarity to the training examples. Now moving on to fine-tuning. The key idea here is simple but powerful. Instead of only giving optimization prompts at inference time, the researchers train the model directly on optimization examples so that it learns how to optimize code internally. Fine-tuning means taking a pre-trained large language model and training it further on pairs of slow, unoptimized code and fast, optimized versions of that same code. Using these examples, the model gradually learns common optimization patterns and techniques directly from data. For this, the authors used the Pi dataset, which contains thousands of real code optimization examples. They fine-tuned models from two major families, Code Llama models and OpenAI GPT 3.5. In this section, the authors also discuss an important challenge, that is, dataset imbalance. Even though the Pi dataset contains tens of thousands of slow to fast code pairs, those examples come from only 1,474 programming problems. Now, why is this an issue? Because the model may end up learning optimization patterns that are specific to those problems, instead of learning optimization strategies that generalize well to entirely new programs. The authors also point out that the data distribution is highly uneven. Some programming problems have a large number of submissions, while others have very few. This means the model sees certain types of problems again and again during training, creating a bias toward those patterns. As a result, the model may perform very well on familiar problem styles, but struggle when it encounters unseen or underrepresented programs during evaluation. To address the dataset imbalance problem, the authors tried a more selective fine-tuning strategy. Along with training on the entire Pi dataset, they also created a smaller, high-quality subset containing 4,085 slow-to-fast code pairs. But these were not chosen randomly. The researchers specifically selected examples that showed the highest performance improvements, meaning the optimized code achieved the largest speedups compared to the original implementations. They also introduced another important constraint. No programming problem was allowed to contribute more than 4 submission pairs. This helped reduce overrepresentation from problems that had a huge number of submissions in the dataset. As a result, the final subset had a much more balanced distribution, with an average of about 2.77 training pairs per problem. Note that, given the high costs of training models through the OpenAI API, the authors used this dataset as a base for fine-tuning experiments with GPT 3.5. Another very interesting strategy discussed in the paper is called performance condition generation. The motivation behind this idea is that a programming problem can usually be solved in many different ways, and those solutions can have very different performance levels. Some solutions may be slightly faster, while others can be dramatically more efficient. Now here's the problem. When a model is trained on a large dataset like Pi, it sees a mixture of both small and large optimizations, but it is never explicitly told which optimizations are actually better or more desirable. So the researchers introduced a clever solution: performance tags. Inspired by recent prompting methods and ideas from offline reinforcement learning, they attached a performance score to every optimized program during training. These tags indicate how close a solution is to the best possible performance for that particular problem. The scores are assigned on a scale from 1 to 10. For example, the top 10% fastest solutions are labeled 10 out of 10. The next 10% are labeled 9 out of 10. And this continues all the way down to 1 out of 10. This means the model is no longer just learning how to optimize code. It is also learning the relationship between certain coding patterns and their performance quality. In other words, the model begins to understand what highly optimized code actually looks like. Then comes the really powerful part. During inference, the researchers provide the input program along with the highest performance tag, 10 out of 10. This effectively tells the model, generate the most optimized solution possible. So instead of passively predicting edits, the model is now guided toward producing high-performance code intentionally. Finally, the last dataset strategy discussed in the paper is synthetic data generation. The main motivation here is cost. Collecting large amounts of high-quality human-written optimization data is extremely difficult and expensive. So the researchers explored whether they could automatically generate new training examples using language models themselves, and this process is surprisingly sophisticated. The first step was to use OpenAI GPT 3.5 to generate entirely new competitive programming problems. To do this, they prompted GPT 3.5 with examples from the Pi dataset, including both problem descriptions and accepted solutions, and asked it to create novel programming tasks. For generation, they used a temperature of 1.0 and top P sampling with P equals 0.9, generating 5 candidate programs per prompt. After generating around 10,000 programs, they performed extensive filtering. Programs that behaved identically to existing Pi problems were removed, along with semantic duplicates. After this filtering stage, they ended up with 3,314 unique synthetic programs. But generating new problems was only the first stage. Next, the researchers used a GPT 3.5 model that had already been fine-tuned on the original Pi dataset to optimize these synthetic programs. So essentially, the model generated new programming problems, and then another fine-tuned model attempted to optimize their solutions automatically. Finally, they kept only the high-quality examples where the optimized version was at least 5 times faster than the original implementation. They also limited semantic duplicates to at most 3 examples. After all the filtering steps, the final synthetic dataset contained 1,485 optimized training pairs. The paper describes this entire pipeline as being similar to self-play and self-instruct methods used in neural program synthesis. In simple terms, the model is helping create new training data for itself, allowing the optimization system to scale beyond purely human-written examples. To sum it up, this is how the entire synthetic dataset generation pipeline looks like. Now moving on to the experiment section, where the authors evaluate how well different approaches actually optimize code. In this section, the paper compares instruction and few-shot prompting, chain of thought and retrieval-based prompting, and finally, fine-tuning strategies with different dataset configurations. The authors also discuss the major takeaways from these experiments and analyze which approaches work best for performance optimization. But before discussing the results, the paper first explains the models, metrics, and evaluation setup used throughout the experiments. For the experiments, the researchers evaluated both open access and private language models. On the open source side, they used code llama models with sizes 7 billion, 13 billion, and 34 billion parameters. On the private model side, the researchers experimented with OpenAI GPT 3.5 and GPT-4. GPT 3.5 was used for both prompting and fine-tuning experiments, while GPT-4 was only evaluated through prompting because fine-tuning GPT-4 was not available at the time the paper was written. Also, Code Llama 34 billion parameter model was not evaluated for fine-tuning experiments. Next, the paper introduces the evaluation metrics used to measure optimization quality. The first metric is percent optimized. This measures the percentage of programs that were successfully improved by the model. For a program to count as optimized, it had to be functionally correct and at least 10% faster than the original code. The second metric is speed up. This measures the actual runtime improvement using this formula, where O is the runtime of the original program and N is the runtime of the optimized program. The third metric is percent correct. This measures how often the generated code remained functionally equivalent to the original solution. To verify correctness, the generated programs had to pass all benchmark test cases. The paper also explains an important evaluation detail. If a generated program was incorrect or slower than the original implementation, the researchers assigned it a speed-up value of 1, meaning no improvement. For benchmarking, all experiments were run inside a GEM5 simulation environment. The programs were compiled using GCC 9.3.0, C++17, and the O3 compiler optimization flag. The authors also discuss their decoding strategy. Instead of generating only one optimized program, they sampled multiple candidate outputs and selected the fastest correct one. This strategy is called best at K. For example, best at 5 means generating 5 candidate programs, and then selecting the fastest correct solution. Let's start with the results for prompting, shown in Table 2. The authors compare 3 prompting strategies: instruction-only prompting, standard few-shot prompting, and chain of thought prompting. One surprising finding is that standard few-shot prompting often performs similarly to, or even worse than, simple instruction-only prompting. For example, GPT 3.5 achieves a 39.16% optimization rate with instruction-only prompting, but only 29.04% with standard few-shot prompting under best at 8. This observation aligns with previous research according to which fixed examples can sometimes bias the model toward a limited set of optimization strategies, preventing it from discovering better solutions for new programs. Another key observation is that chain of thought prompting consistently performs better than the other prompting methods, especially for larger models. For instance, CodeLlama 34B improves from an optimization rate of 18.92% with instruction-only prompting to 19.63% with chain of thought prompting under best at 8. The improvement is even more noticeable for GPT 3.5, where chain of thought achieves the best prompting performance with 43.05% of programs optimized, 1.60 times average speedup, and over 91% correctness. Interestingly, GPT-4 performs better than GPT 3.5 when generating a single candidate solution, but slightly underperforms GPT 3.5 when multiple samples are generated using best at 8. Next, the authors evaluate their dynamic retrieval-based few-shot prompting strategy, which is one of the key contributions of the paper. Instead of using the same fixed examples for every optimization task, the model retrieves the most relevant optimization examples from the Pi dataset and includes them in the prompt. The results are shown in the table using the preferable setting of k equals 4 retrieved examples. The improvement over standard prompting is substantial. Across all model sizes, retrieval-based prompting consistently outperforms the baseline prompting strategies we discussed earlier. For example, CodeLlama 34B improves from a 1.30 times speedup with chain of thought prompting to a 2.43 times speedup with dynamic retrieval. Similarly, GPT 3.5 improves from a 1.60 times speedup to 2.19 times speedup. The biggest gains are seen with GPT-4. It successfully optimizes 76.07% of programs and achieves an impressive 3.93 times average speedup, making it the strongest prompting-based approach in the paper. These results suggest that when the model sees examples that are similar to the program it is trying to optimize, it becomes much better at discovering effective performance improvements. One trade-off the authors note is that pursuing larger speedups can sometimes slightly reduce correctness. Now let's move on to the fine-tuning results shown in the table. An interesting observation is that training on the smaller, high-quality dataset often performs better than training on the entire dataset. For example, the high-quality fine-tuned GPT 3.5 model achieves an impressive 6.74 times speedup and successfully optimizes over 86% of programs under best at 8. Next comes performance condition training, where optimization quality tags are added during training. For CodeLlama 13B, performance condition training boosts the optimization rate to 66.56% and achieves a 5.65 times speedup, substantially outperforming the previous fine-tuning technique. The authors attribute these gains to the performance tags, which help the model distinguish highly optimized solutions from merely acceptable ones. The final strategy is self-play, where synthetic optimization examples are added to the training data. Adding synthetic data generally increases the percentage of programs that can be optimized, suggesting that the additional examples help the model generalize to unseen programs. The best overall model in the paper is GPT 3.5 fine-tuned on the high-quality dataset augmented with self-play data. This model achieves 87.63% optimized programs, 6.86 times average speedup, and over 95% correctness. Finally, the authors compare their best model against the fastest human-written solutions available in CodeNet. For the Pi dataset, the best human solutions achieve a maximum speedup of 9.56 times, while the model achieves a slightly higher speedup of 9.64 times. Finally, let's look at the discussion section, where the authors summarize the key takeaways from the paper. The first takeaway is that open source models can be surprisingly competitive with proprietary models when the right adaptation techniques are used. For example, CodeLlama 34B with retrieval-based prompting achieves performance that is quite close to GPT 3.5 using the same strategy. Similarly, a fine-tuned CodeLlama 13B with performance condition generation approaches the performance of GPT 3.5 trained with synthetic self-play data. The author suggests that applying these techniques to a larger CodeLlama model could narrow the gap even further. The second takeaway is the comparison between prompting and fine-tuning. While prompting can improve optimization performance, especially when combined with retrieval, fine-tuning consistently delivers much stronger results. The third takeaway is the effectiveness of retrieval-based few-shot learning. Among all prompting methods, dynamic retrieval provides the largest performance gains. This shows that providing relevant optimization examples is far more useful than relying on fixed prompts alone. The final takeaway is the effectiveness of performance condition generation. Adding performance tags during training dramatically improves the model's ability to produce highly optimized code. For CodeLlama 13B, performance condition training increases the optimization rate from 47.75% to 66.56% and boosts speedup from 3.43 times to 5.65 times. So, if we summarize the entire study in a few points, Retrieval-based prompting is the strongest prompting strategy. Fine-tuning substantially outperforms prompting. Performance condition generation provides major gains during fine-tuning. Synthetic self-play data further improves generalization. And with the right training techniques, open-source models can become competitive with proprietary models for code optimization. And with that, we arrive at the conclusion of the paper. The authors view this work as an early step toward a much bigger goal, using large language models not just to generate code, but to actively improve the efficiency of software. Traditionally, performance improvements have relied heavily on advances in hardware and compiler optimizations. However, this paper demonstrates that LLMs can operate at a higher level of abstraction, discovering algorithmic and implementation improvements that go beyond what traditional optimizing compilers can achieve. By combining program optimization with correctness verification, the researchers show that language models can automatically transform working programs into significantly faster versions while preserving their behavior. And that's what makes this work so interesting. It's not just about generating code, it's about teaching AI to make code better. And that wraps up our deep dive into learning performance improving code edits. If you found this paper breakdown useful, don't forget to like the video, subscribe to the channel, and let me know in the comments which research paper you'd like me to cover next. Thanks for watching, and I'll see you in the next one.